In this video, we'll discuss the basics of Pytorch syntax and usage. Please open the Pytorch Foundations notebook in Colab and use it to follow the examples. We teach Pytorch in this course rather than TensorFlow, as Pytorch is much easier to get started with and is fast for prototyping. This is because it offers a much simpler API with syntax which is designed to be as close as possible to basic Python. It's also much easier to debug as it implements its computational graphs dynamically, allowing code to be run in an interpreted line-by-line fashion like regular Python. TensorFlow, on the other hand, traditionally creates static computation graphs, which effectively need to be compiled before running. This historically makes it faster and more adaptable to run across multiple devices. However, this choice created a situation where TensorFlow was originally very difficult to debug. Pytorch, on the other hand, because it's so deeply integrated with Python, is simple to debug using regular Python debuggers such as those available through the Spider or PyCharm IDEs. It's probably only fair, however, to highlight that TensorFlow has recently had a major overhaul to make its syntax simpler and allow for dynamic computations similar to Pytorch. So nowadays, the differences between the frameworks are not so great. However, as this is just one of many complete overhauls of TensorFlow over recent years, this hasn't added to its popularity. Accordingly, Pytorch has been much more commonly used for research development, as shown by its increasing dominance over TensorFlow in codebases linked to papers from major research conferences. Therefore, for those of you wanting a local install of Pytorch, either so that you can debug locally using your IDEs or because you have an NVIDIA GPU on your local machine, you just need to go to the website, which automatically detects your local operating system and offers a suitable install, printed here for install with Anaconda. Note that because I have a Mac laptop without an NVIDIA GPU, it won't install the GPU version, which is what it means by not supporting CUDA. Moving on to basic syntax, to emphasize the similarity of Pytorch and Python, or more specifically NumPy, let's look at generating a random array of size 2 by 2 by 2. This example is given in your tutorial notebook. You can hopefully see for yourself that the syntax is very similar. In NumPy, it's numpy.random.rand, and in Pytorch, which you import as torch, it's torch.rand. These being random arrays, of course, the output itself isn't expected to be the same. We can also see that the two arrays are indexed in the same way. And reshaping is very similar. And conversion to and from Pytorch tensors to NumPy is straightforward. Here's an example of type conversion. For example, you could use this to change from a float or an int to a double. Finally, you do also have another option for reshaping, which is to use view, applied directly on the tensor itself. So x here is created as a torch tensor, and then you can call x.view directly. The -1 here tells it to infer the length of the dimension from the total size of the array. So in other words, shape 1 - 1 will stretch the tensor into a row vector with length equal to the total number of elements in the original array, which in this case is 9 because it's 3 by 3. Now pause the video and run through these lines of code in your notebook to check that you are comfortable with them. Then have a go at exercise 1, which investigates the differences between Pytorch and NumPy broadcasting. Having said all this, we should be less interested in what makes NumPy and Pytorch similar and more focused on what the key differences are, which make Pytorch tensors so suited to deep learning. This is their support for automatic differentiation and dynamic computation graphs. Remember our computation graphs from lecture 2. Pytorch creates these dynamically, restarting from scratch at each iteration through the input data to give maximum flexibility during training. The nodes of the graph store the forward and backwards operations needed to perform forward and back propagation. The leaves of the graph are therefore the input tensors which store the input data. The root of the graph is the output tensor which stores the loss. The gradients therefore are traced backwards from root to leaf using the chain rule. In total, an overview of the Pytorch approach, which you will do well to remember when you start to build your own networks, is that we first need to define an architecture we want to train on. We will do this by creating a network class based on a very specific structure that we will look at in the next video lecture. We must then choose which loss function we want to use and which optimization strategy, where loss functions and optimizers will be introduced in the next video but discussed in more detail next week. Once we have all this, we can perform a forward pass to estimate the loss for this specific pass through the network, given the input data and existing values of the weights. So we forward propagate through the graph from leaves to root. Next, we have to tell Pytorch to backpropagate. Using partial derivatives that it calculates as it puts together its dynamic graph, it will plug the values of the variables in for that iteration and estimate the gradient. Once it's done this, it can update its weight tensors using its chosen optimization strategy and learning rate. Then it starts the process from steps 2 to 5 again until convergence. Pytorch does all this using its autograd class, and is supported by the fact that Pytorch tensors don't just store the data, they also keep a record of the gradients and gradient functions for each tensor in order to support backpropagation. For example, here is a simple Pytorch computation graph for a multiplication operation, z equals x times y. The green boxes represent the variable tensors and the purple box represents the forward operation. The variable tensors store not just data, but the following attributes. First, requires grad. This tells the tensor whether to track its gradient. This is automatically set true for tensors which result from some operation, here a multiplication. So requires grad is set true for z. Grad, on the other hand, stores the value of the gradient and will be none initially. And grad function stores the backwards operation through that node of the graph. Finally, is leaf will be true if the tensor represents a variable initialized by the user, i.e. x or y, but false if it's the output of an operation, for example z. Next, when the user specifies a backwards pass using .backwards, the graph updates the gradients only for those for which requires grad is true and is leaf is true. So here this applies just to x, where grad function is only true for tensors which result from operations, in this case z. Specifically, the grad function of z is the gradient of a multiplication termed more backward, and this is estimated with respect to x. So the output is stored in the grad attribute of the x tensor. Because the gradient of z with respect to x is y and y is initialized as 2, the gradient stored in x at this iteration will also be 2. To see how this works, please go to the notebook and run through the example for this simple function L, which nonetheless requires computation using the chain rule. Print out the gradient of the input leaf tensor x and the grad function associated with the output tensor. Consider checking the attributes is leaf and requires grad for each of these tensors. Optionally, if you're feeling confident with the math, you can go on to prove the gradient calculation is correct through hand computation of the derivatives using the chain rule. Note that if you need the vector gradient of the sum operation, you can get it from the following reference. You may also want to try a different function. Please pause the video and complete that task. Next, moving on to the torch.nn module, this contains all the functions that you will need to build a neural network, including fully connected layers, convolutions, and pooling operations. Some of these we will discuss in more detail next week. Here is an example of a fully connected or linear layer. Using the notation from the first lectures, this means that it outputs the equivalent of the z equals wx or wf operations. Its input arguments are the total number of input features, which would equate to the number of features of input data for a single neuron classifier, or the number of neurons in the previous layer. The second required argument is out features, which equals the number of neurons in the current layer. It also has bias equal to true by default. We can apply this to some simulated input data, which we'll create as a 3 by 100 by 100 3D image. But to use it with a linear or fully connected layer, we first need to stretch that out into a vector using the reshape operation. Our number of input features is then equal to the total number of elements of our data, which is 3 times 100 times 100, and we choose output features as 10 neurons. Also, importantly, our tensors must be cast as float, as Pytorch only supports gradient estimation for floating point tensors. Please run this in a notebook and check that you're comfortable with how it works. The next thing we need to discuss is nn.functional. So this module provides building block functions which should be considered whenever you have operations without any trainable weights. For example, the ReLU function or other activations, interpolation or average pooling. They are not, however, suitable for linear or convolutional layers, as these learn trainable parameters and behave differently at train and test time. For these types of operations, you should instead be using the nn.module functions. Finally, for this lecture, I want to discuss the dataset and dataloader classes. In deep learning, input data must be collated and pre-processed, for example through normalization, and then prepared into batches before being fed into the neural network for training. Optionally, it can also be augmented or transformed in different ways to simulate the appearance of more data. In Pytorch, these operations are all dealt with within bespoke dataset classes. Once we have the data prepared, however, we need to feed it into the network, and this is the role of the dataloader. It supports continuous shuffling of the data to prevent memorization and can schedule data loading in case the whole dataset is too large to hold into memory in one go. Therefore, for each new network, you need to create your own dataset class, which will inherit from the template class provided by Pytorch. This must overload the base class functions len and getItem, such that the len of your custom dataset will return the number of examples in the dataset, be it train or test sets. You can create different instances of your class for each. GetItem is then the main function that will pre-process and prepare the data for batching. Note that for supervised learning, you will need it to return both a sample and a label. Incidentally, init, the constructor, typically sets such things as the path to the data or reads in a CSV file containing this information. It also saves the transform object, which if passed is a class with member functions which augment or change the appearance of each sample. Outside of these basic requirements, there are no other constraints, so you're free to write these functions as you choose and perform pre-processing suited to your problem. However, the getItem function does expect the argument IDX, which would be an index which controls which one of the samples are returned from your dataset. Taking this example from the official Pytorch tutorial, therefore, this uses the IDX to return a row of the CSV file, which is initially passed to the constructor in red there. The ID is then used to generate the path to one of the image samples and then used to load it. The labels corresponding to this image are then also taken from the corresponding row of the CSV file, and the data is optionally augmented. Note the option to augment is a choice. It will occur if you pass a transform object and won't if you don't. This is because while you may want to augment the training data, you typically don't want to augment your validation or test data. In terms of the types of transformation you might see, these augmentations can include flips of your image, crops, or affine or non-linear deformations, changing the shape and appearance of your image, but whichever you use should make sense for your data. In other words, you should augment your dataset using transforms which generate new images which remain plausible in the context of your problem. For example, creating flipped images of people's torsos makes little sense, as you rarely see someone's heart on the other side of their chest. Next, the dataloader is an iterator which collates data into batches, shuffles input data to prevent memorization, and coordinates parallelization of pre-processing tasks through scheduling. While you are required to create bespoke dataset classes which overload from the base class, you will typically just use the generic dataloader and call it in the following way, telling it whether you want to shuffle and what the batch size should be. Having said all that, while you will need to create your own dataset classes for your own data, Pytorch does come with a number of popular benchmarking datasets. For example, the MNIST dataset, which represents 2D images of handwritten digits. To download these, you need the Torch Vision module. The full list of available datasets is searchable here. To download MNIST, for example, you need the following lines of code: importing the dataset module from Torch Vision and the module that supports transformations of your data. You can call the MNIST data constructor then as follows, noting that the dataset has already been separated out into train and test sets, so you need to specify paths separately for these. If you need to download it, you then can pass the argument download equals true. And for your training data, you must pass train equals true, whereas for the test dataset, train should be specified as false. Here, the only transform specified is to transform the image from a PIL image format into a Torch tensor. You can then try out some of the dataset functions, specifically printing out the number of examples in each of the train and test sets, shown here only for train. There are 60,000 training examples. We can also take a sample from the dataset using an ID, here 0, and this returns the first training image and its scalar label. In this case, the image of a number 5, with label the integer 5. All MNIST images have shape 28 by 28. Then we can create separate data loaders for the train and test datasets as follows. These are given batch size 128 here. Note, we don't need to shuffle the test data. You can see that the first argument as well is the datasets that we've just created. Once again, we've created separate ones for training and test. We can then iterate through the dataset, selecting batches using the inbuilt iter or enumerate functions as shown. The difference between these being that enumerate will also return the batch number. Alternatively, to just return one batch, you can instead use the next function as shown. We can use this to check the batch shape, for example. So that's it for Pytorch basics. In summary, Pytorch is an easy-to-use and flexible deep learning coding framework which is designed to be very similar to Python. It's therefore interpretable, capable of running line by line, which makes debugging easier, and it achieves this through building computation graphs dynamically, line by line, and refreshed at each new iteration through the training data. Pytorch computation graphs are constructed using its autograd class, using the fact that Pytorch tensors not only store data but also gradient functions and the gradients themselves. Pytorch has several different classes or modules for building and training networks. Of these, torch.nn contains the major building blocks of your networks, the linear or convolutional layers, for example. Torch.nn.functional, on the other hand, defines functions with no trainable parameters, for example, activation layers. Torch.nn and torch.nn.functional therefore allow you to write your network classes which define your architectures, but to train you need to pre-process and batch up data. This is done with the dataset and data loader classes. Typically, you don't need to do anything to the default data loader, just use it. On the other hand, while Pytorch provides a few common datasets, typically you will need to create bespoke dataset classes which overload the Pytorch base class. In particular, the init, length, and getItem functions. These support loading and pre-processing data, including normalization and data augmentation where needed. Please complete the Keys quiz to reinforce the key points from this lecture, and during Thursday's tutorial, please go through exercise 3 on creating a bespoke dataset class. You may want to read through the example in the notebook before then.